Good morning, ladies and gentlemen. Today's topic of presentation is fast quality over AMDF-based pulsate estimation from compressed PPG measurements for wearable vital signs monitor. The authors of the paper, myself, Shivaranjani, PN, and M. Shabarimali Manigandan from the Department of Electrical Engineering, Indian Institute of Technology, Palakkad, India, and Linga Reddy, Sangama Reddy, collaborating with us from the University of Palakkad. So the course of presentation, I'll be briefing on the following topics. In the introduction, I would like to brief about the photoplethysmogram, which is a non-invasive optical technology to detect blood volume changes for heart rate and heart health monitoring. We say the PPG technology is having an upper hand over the conventional ECG-based heart health monitoring because of the easiness and simplicity of PPG acquisition and processing. The PPG pattern that you see on the right is obtained based on the blood volume changes that is calculated based on the amount of detected light. The next is the average magnitude difference function of the AMDF function. The AMDF function is shown on the right for the PPG signal shown above. The AMDF function, like the autocorrelation function, is used for the pitch period estimation of speed signals in literature. In this research, we have used AMDF for the pulsate estimation because of the simplicity of computation of AMDF, as no multiplications involved, as clear from the equation. In the literature review, we had done rigorous literature review to find the existing motion artifact removal methods and various methods used in literature for signal quality assessment of PPG signals. And we found various machine learning and deep learning based signal quality assessment method using different features extracted from PPG signals. From this literature survey, our inference was a need to develop a reliable and energy-efficient pulsate estimation method for wearable health monitoring devices under corrupted PPG signals and pathological PPG patterns. The limitations of the existing method or the existing wearable health monitoring devices is the presence of false alarms due to unavoidable circumstances and like artifacts and corrupted signal due to contact pressure, sensor movements, hand body movements, ambient light, interference, skin tone, etc., and false alarm due to respiration-induced variations in the PPG signal. And obviously, the most important challenge is always the energy constraint and power constraint for wearable health monitoring devices. So the major contribution from our side is that we are proposing a compressive sensing-based pulsate estimation method to reduce computation complexity, wherein we will be using the deterministic block binary diagonal or the DBBD sensing matrix to enable pulsate estimation directly from the CS measurements without computationally expensive reconstruction process. We will be presenting a simple pulsate estimation based on the AMDF waveform, which does not require multiplication, like autocorrelation or the other signal processing techniques in pulsate estimation study. We have explored a signal quality assessment approach as well, which we have incorporated using the features extracted from the AMDF instead of ML approaches, which increases the computation load. We are also evaluating the performance of the proposed method in a very wide variety of normal and pathological PPG signals. This is the block diagram of the proposed CS PPG based pulsate estimation method. The different steps, major steps are the compressed PPG sensing, pre-processing, AMDF computation, first the minimum peak finding and pulsate estimation, and EMDF feature-based signal quality assessment. The various steps, the output of various steps are shown on the figure on the right. The very first step, compressed PPG sensing for a signal x of length n is governed by the equation y equal to phi x, where y is the CS measurement vector of length m, where m very, very less than m. And phi is the sensing method of length m, of size m cross n. There are wide variety of sensing matrices that are studied in literature. Based on our study, we found that the deterministic block binary diagonal sensing matrix that is shown on the last can be used for directly finding the pulse rates without the computationally complex reconstruction process, because the shape and characteristics of the original PPG signal is preserved in the compressed measurement when DBBD sensing matrix is used. So we are using the DBBD sensing matrix with a compression factor of 5 in the study. The second step is a pre-processing. We will be using the fifth order Chebyshev type 1 high-pass filter of cutoff frequency 0.5 Hz for baseline removal. 0.5 Hz is set as the lower cutoff frequency based on the 30 to 300 beats per minute, which is the normal, which is the human pulse rate range. The third step is the partial AMDF computation, wherein in the study we are using partial AMDF computation only for a signal of any length. We will be computing the AMDF only for the useful pulse rate range of 30 to 300 beats per minute that is found from the equation lag equals 16 to SFI pulse rate. So this partial AMDF computation reduces the computation complexity for the fourth step is the minimum peak finding as shown in this figure for a PPG signal as shown in A1, that AMDF is computed as B1, and the first minimum peak of the AMDF is found in the study using the negative zero crossing point based method. From this minimum lag, the pulse rate is estimated as PR equal to 16 to FS by lag. And as very clear from this figure, the AMDF pattern of a clean PPG signal has a periodicity and a characteristic shape, whereas for a PPG signal that is corrupted by noise or motion artifact, the characteristic shape or the characteristics of the AMDF is changed, which is the basis for the signal quality assessment that we have developed. So for the AMDF feature extraction based signal quality assessment, we are extracting the following features, that is the pulse rate, number of threshold crossing of the signal for a threshold of 0.1 and minus 0.1 for a normalized signal, number of local minimum peaks in the AMDF, then the first and the second minimum peak amplitude of the AMDF, and the distance between the minimum peak locations. And based on these features and based on the characteristic shape of the AMDF, we have developed an algorithm for the signal quality assessment where we will be classifying the signal as noisy or clean or acceptable and unacceptable. So for the result and discussion, the evaluation database and performance metrics database we have formed from the following 5 widely popularly used standard databases, that is MIMIC, Capnobase, BIDMC, CSL, and RIST PPG exercise database. We have collected around 7,000 segments of 10 seconds from all these 5 databases for a test duration of 10 seconds and 60 seconds and a sampling frequency of 125 Hz. In the test database, it includes different kinds of pathological PPG signals, arrhythmias, noise, and artifacts. And the pulse rate estimation performance is evaluated using the widely used performance metrics like mean absolute error, root mean square error, and bland odd-man ratio. Signal quality assessment performance is evaluated using sensitivity, specificity, and accuracy. The table shows the performance of the signal quality assessment method for 10 second and 60 second segments based on true positive, false negative, false positive, and true negative. The most important inference from this table is that the performance of performance or accuracy of 60-second segments is less than 10-second segments because the performance is degraded due to short duration noise portions of for 60-second segments. And also for the RIST PPG database, which had almost no clean segments, there were about 185 segments which were classified as clean by our algorithm. And by further investigation, we found that the pulse rate estimation error for most of these segments were also acceptable only. But though it had acceptable pulse rate estimation error, they cannot be used for measuring other PPG parameters and clinical indices. The next performance comparison is using database-wise performance comparison in terms of mean absolute error, VAR, and RMC for 10-second and 60-second segments for different databases with and without signal quality assessment for original and CS PPG measurements. From this table, the inferences are that the original PPG-based method had better performance over CS PPG-based method. However, the CS PPG-based method uses only 1/5 of the computational operations as compared to original signal. Hence, the performance of CS PPG-based method is very much comparable to the original PPG-based method. The next inference is that the 60-second data had better performance compared to 10-second segments, as clear from the performance indices. And also, the signal quality assessment has improved the performance considerably compared to the performance without signal quality assessment. And also there is an inference that the averaging metrics do not reflect large estimation error, and the effectiveness of the pulse width estimation method in terms of number of PPG segments within the estimation error range is important to highlight the large estimation errors. So in this table, we are highlighting the performance comparison of pulse width estimation with CS and original PPG in terms of estimation error ranges. From this table, we can find that for CS PPG measurements, the number of segments which has error greater than 10 is less compared to original PPG for both 10-second and 60-second segments. And as per the American standards, the estimation error should be within 10% of input rate or within plus or minus 5 beats per minute. So the proposed method had a better performance as compared to the original PPG segments in terms of number of segments which had estimation error within 10 beats per minute. And we also see that number of segments which has error 0 is less for CS PPG. However, the number of segments which has error within 5 beats per minute is almost equal or better for CS PPG. And for the conclusion, we had presented a past quality aware AMDF-based pulse width estimation framework in compressed sensor domain. The performance of CS PPG-based pulse width estimation method with DBBD sensing metrics was evaluated and compared with original PPG-based estimation method in terms of well-known metrics and estimation error range control. AMDF-based pulse width estimation is robust for PPG signals collected with low level to medium level of motion artifacts, and the CS PPG-based method had only 1/5 of the computation operations compared to that of the original PPG-based method, which is the greatest highlight of this proposed method. In the future direction, we will be implementing the proposed quality-aware pulse width estimation method in resource-constrained computing platform to perform energy consumption analysis. We would like to acknowledge the contribution of the Research Council of Norway for funding our research in the Indian Institute of Technology, Palakkad. These are our references. Thank you.